In this module, we will see the final algorithm for converting an LTL formula into a Bucci automaton. In the last module, we saw what are called formula expansions. Given an LTL formula and a word, in the formula expansion, we evaluate every subformula at every position in the word. This gives us some kind of an infinite table. We also saw the properties satisfied by these formula expansion. For example, if x of some formula is 1 here, then in the next position that formula should be 1. Similarly, we saw and, not, until compatibility conditions. We now want to construct an automaton whose states are these columns, and the transitions are given in such a way so that on a word which belongs to the language of this formula, the run of the automaton looks like the expansion. We want the automaton to guess accepting expansions. We will see an example and then we will give you the final construction. Let's start with the example P1 until P2. What are the possible columns in the expansion of P1 until P2? The subformulae are P1, P2, P1 until P2, and each of them could be either 0 or 1. So in all, we have 8 possibilities for a column in the expansion. However, recall that there are some compatibility conditions. In particular, look at the until compatibility condition. It says that if phi1, phi2, phi1 until phi2 are there as subformulae, then these are the possible values in the columns. Let's see. What about 0, 0, 0? 0, 0, 0 is a possibility. It says that phi1 is 0, phi2 is 0, and phi1 until phi2 is 0 as well. What about 0, 0, 1? 0, 0, 1 is not possible because this says that P1 is 0, P2 is 0, but P1 until P2 is true in that position. This cannot be the case. So, this cannot be a potential column in the expansion, so we remove that. What about 0, 1, 0? This says that P2 is true. If you look at the compatibility criterion, if phi2 is true, then phi1 until phi2 has to be 1. And here P2 is 1, but P1 until P2 is 0. This is not possible, so we remove that vector as well. So that cannot be a possible state. What about 0, 1, 1? This is possible. When you have 1 here and 1 here, either this is 0 or 1. So this is possible. What about 1, 0, 0? It says that 1, 0, 0 is potentially possible, but if this is the case, then in the next step, the phi1 until phi2 should be 0. That is fine. We will take care of the next step later, but for now, 1, 0, 0 is a possible column. So we keep that. 1, 0, 1 is again possible. Again, if 1, 0, 1 occurs as a column, then there is a condition on the next step. We will not bother about it now. We know that 1, 0, 1 can potentially occur as a column. So we keep 1, 0, 1. What about 1, 1, 0? If phi2 is 1, then phi1 until phi2 should be 1. So this cannot be the case. This is not a compatible column, so we remove it. 1, 1, 1 is possible. So these are the blocks which can potentially occur in an expansion of P1 until P2. You can go back and check the expansion of P1 until P2, the example that we had given. Every column would be one of these. These are called compatible states. We will be constructing an automaton using states given by these columns. Before giving the actual construction, let us try to see what the automaton should do on a word. Let's assume that there is a separate initial state Q0, and this automaton should accept words which satisfy P1 until P2. And how are we going to do that? We are going to guess the accepting expansion for the word. Suppose the first letter that is read is P1. How does the first column look like? P1 should be 1, right? So it could potentially be this one or this one. Since P2 is 0, it can be one of these two states. Since we are guessing and accepting expansion, the automaton guesses that the rest of the word is going to satisfy P1 until P2. And so from Q0, the automaton should go to 1, 0, 1. The automaton is making a guess that the rest of the word will satisfy P1 until P2. If it does not satisfy P1 until P2, the automaton should be blocked. Let us see. So now we are in state 1, 0, 1. Suppose the next letter that is read is P1 again. If you look at the column, the evaluation would have been 1 because of P1, 0 because there is no P2, and now by the criterion, by the until compatibility criterion, if you have 1, 0, 1 here, the next step should have 1 here. So the automaton will choose the state 1, 0, 1. This says that P1 until P2 is going to be true, and currently P1 is true. So right now only P1 is true, so still P1 until P2 is going to be true. That's what the automaton has guessed. Now, if it still sees P1, it will keep staying in this state. Now, what if it sees P2? Because it sees P2, this entry is 0. This is the entry for P1. This is 0. This is going to be 1. And of course, this is going to be 1. Because if this is 1, then this has to be 1. Just look at the word P1, 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 P2 and try to build the expansion for this word. You will see that this will be the first column, this will be the second column, this will be the third column, this will be the fourth column. So the automaton had guessed that at some point P2 will come, and it has now seen P2 and it has verified this guess. Suppose it sees an empty letter, the letter consisting of the empty set. This and this have to be 0. Here there is no choice. It has to be 0 because P1 until P2 cannot be true in this position, as P1 is false and P2 is false. Now at P1, suppose it sees P1, this has to be 1, this has to be 0, and here it can make a guess. It can guess whether in the rest of the word P1 until P2 is going to be true or not. Here we have assumed that it is 1, and then now the automaton has to verify if P1 until P2 is true. Let's see one more example of a word. Initial state is Q0. On seeing P1, the automaton has two choices. It can go to 1, 0, 0 or 1, 0, 1. However, we enforce the automaton to go to 1, 0, 1 because we want to recognize accepting expansions only. So the automaton makes a guess that P1 until P2 is going to be true now. Suppose it sees the empty letter. It knows that P1 until P2 is going to be true. That means in the next step, either P1 should be true or P2 should be true. So if it sees this, it should not be able to take the next transition. So from this state, there should be no transition on this empty letter. there should be no compatible transition that reads this letter. So this is the rough idea. The states of the automaton are going to be these 5 along with Q naught. Initially, on reading some letter, the automaton goes to the corresponding state with the last entry being 1. It assumes that in the rest of the word, P1 until P2 is going to be true. And based on the compatibility criteria, the next transitions should be defined. In particular, if the automaton reads P1 followed by the empty letter, it should not be able to move. However, if it reads P1, 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 P2, it should come up to this state, and here it should go to this state, and here it should go to this state, etc. Let us now give the automaton construction. The states are Q0 and these columns. These were the compatible states. This is the until criterion. We should give our transitions based on this until criterion. This says that if 101 is here, then there is some condition on the next step. Similarly, if there is 100 here, there is some condition on the next step. First, from Q0, what should the transitions be? The transitions should go to states where the last entry is 1. Because in accepting expansions, the last row of the first column is 1. We want our automaton only to look at accepting expansions. So, from Q0, if it sees just P1, it goes to 1, 0. This is because of the word compatibility criterion. If you have P1, then the P1 entry should be 1 and the P2 entry should be 0. And of course, the last entry, we want it to be 1. If it is P2, then it goes to 0, 1, 1. If it is P1, P2, it goes to 1, 1, 1. If you look at any accepting expansion that starts with P1, P2, then this will be the first column. Similarly, if you look at any accepting expansion that starts with P2, this will be the first column, and similar for this thing. If the accepting expansion starts with the word P1, then this will be the column. Now, let us look at this state. What are the outgoing transitions for this state? If you look at the until compatibility criterion, it says that if 101 occurs, then in the next step, this entry has to be 1. So, from this state, you can either stay in this state or go here or go here. You cannot move to these states. That is what is depicted here. If you see P1, if the next letter that is read is P1, then you stay in this state. If the next letter that is read is P2, you jump to this state. If the next letter that is read is P1, P2, the automaton jumps to this state because P1 and P2 both are true. And the until compatibility criterion asks that the last letter has to be 1. Let us now look at this state. When you have 1, 1 here, there is no condition on the next step. The next step could be any of the possibilities. We just need to ensure word compatibility. Let us see. If you read the empty letter, there is only one state which can be reached. This is 0, 0 and 0. What about letter P1? You can either go to 101 or 100. The automaton is, if it goes to this state, the automaton is making a guess that the rest of the word satisfies P1 until P2. However, if the automaton moves to this state, then it's making a guess that the rest of the word does not satisfy P1 until P2. Here there is non-determinism. Okay, there are two choices. On the letter P1, the automaton can either go here or it can go here. Now, if it reads P2, it stays here. If it reads P1, P2, it goes here. That is depicted here. Let us look at this state. Similar to this state, there is no condition on the next step. So when you read the empty letter, you go here. When you read P1, there is a choice. Either you can go here or you can go here. If you read P2, you go here, and if you read P1, P2, you stay here. They are these transitions. Now let us look at this state and let us try to give the outgoing transitions from this state. Look at the compatibility criterion. From 0, 0, 0, there is no condition on the next step. So if you read empty, you stay here. If you read P1, you go here or here. If you read P2, you have to go here. And if you read P1, P2, the automaton goes to this state. Now finally, let us come to this state. Here there is a compatibility criterion for the next step. It says that if the current vector is 1, 0, 0, the current column is 1, 0, 0, the next step has to be 0 in this entry. This says that if P1 is true here, but if P1 until P2 is false here and P2 is false here, it cannot be the case that P1 until P2 becomes true here. See, if P2 is already false here, the only hope of satisfying P1 until P2 is to have some P1s here and then finally P2. Now, if this entry says that P1 until P2 is true, then this also has to be true. So in particular, if you have 1, 0, 0, the next step you should see only 0. So from here there are only two choices. Either you can go here or you can stay here. So this you go if you read the empty letter, and you stay here if you read the letter P1. So we have given the states and transitions of the automaton. So there are paths in this automaton. One path is you read P2, and if you keep reading P2, then the columns are going to be like this. So what you can check out is give some infinite word and then try to find the runs of this automaton on that infinite word. You will see that if that word satisfies the LTL formula, then there will be a way of reading the entire word. However, if the word does not satisfy the LTL formula, then this automaton will not be able to read after some point of time. For example, the word P1 followed by the empty letter does not satisfy P1 until P2. So you see P1, empty letter, empty letter, empty letter, and so on. From Q0 on P1 you go here, and here there is no transition out of the empty letter. We had seen this example previously. Suppose you have the word P2 followed by the empty letters, then that is possible because you read P2 and then you go to this state on reading the empty letter, and then you can keep reading the empty letter any number of times. The moment you read P2, you know that the word satisfies P1 until P2. There is still one condition left. Note that we have not mentioned what are the accepting states in this automaton. Recall the until eventuality condition. For example, look at this path P1, 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 P1 and so on. The word which consists only of P1 can be read by this automaton, but it should not be accepted because you are never seeing P2. The until eventuality condition will not be satisfied. Note that the condition says that if it cannot happen forever that phi1 until phi2 is 1, phi1 is 1 but phi2 is 0. Now how do we eliminate words of this form? Here we will make use of accepting states. We will mark the rest of the states as accepting. The states where either phi1 until phi2 is 0 or the states where phi2 is 1. You can safely loop in these states. You can see these states infinitely often. There is not a problem. However, if you loop in this state forever without visiting any of these states, then that word should not be accepted. Now look at this word P2 followed by empty letter and so on. That is fine. P1, P2 followed by P1 followed by P1 is fine because you have already satisfied P1 until P2. And then if you keep reading P1s, that's not a problem. Let me repeat. So up to this point, we added compatible states and we added transitions that satisfy the compatibility criterion. However, by doing this construction, we have still not satisfied the eventuality condition. For example, this word P1, 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 P1 and so on, this is a word which is not in the language, and this is not an accepting expansion because it does not satisfy the eventuality criterion. From this construction, we need to filter out only those runs which mimic accepting expansions. To do that, recall the eventuality criterion. It says that it cannot happen forever that you see a state where phi1 until phi2 is 1, phi1 is 1 but phi2 is 0. To ensure this criterion, we will make this as a non-accepting state. And states where phi1 until phi2 is 1 and phi2 is 1 are safe. And states where phi1 until phi2 is 0, they are also safe. Only the states where phi1 until phi2 is 1, phi1 is 1 and phi2 is 0, these are the states which cannot keep occurring forever. That is, continuously they cannot occur. So, apart from those states, you make the rest of the states as accepting states. Now look at any run in this automaton, any accepting run in this automaton that will correspond to a word which satisfies P1 until P2. This is the automaton corresponding to the LTL formula P1 until P2. Note that we had given an easier automaton for P1 until P2. However, in module 1, we were not giving a mechanical way of constructing the automaton. It was not an algorithm. We were making use of our intuitions to create different automata for different LTL formula. Now, this will be a standardized algorithm for any arbitrary LTL formula. And that algorithm will give us this automaton for P1 until P2. Let's see one more example. We will not construct the entire automaton for xp1 until p2, but we will see the steps towards constructing the automaton. Firstly, the subformulae are p1, p2, xp1, xp1 until p2. So if you had written an expansion for this formula, you would have seen these as your columns. So these can take either 0 or 1, 0 or 1, 0 or 1, 0 or 1. So in principle, there are 16 such states, 16 such possible values for columns. However, some of them would be incompatible. Let's see some potential runs of the automaton for xp1 until p2. It starts with q0. If it sees the empty letter, it has to go to a state where the first two entries are 0. This slot is for xp1. At this position, the automaton can only make a guess whether in the next step p1 will be seen or not. Suppose the automaton guesses that xp1 is 1. Let us see what happens. But before that, what about this slot? In an accepting expansion, we will always need that to be 1. Okay, from Q0, we let the automaton guess that xp1 until p2 is going to be true. And so xp1 also needs to be true. Now, since we have made that xp1 is true here, it has to read a letter that contains p1. And it goes to a state where p1 is 1, p2 is 0. It still has to maintain xp1 to be 1 because we have to maintain that xp1 until p2 should be true. So the automaton has guessed that xp1 until p2 is true. So this entry has to be 1 till it sees a P2. So XP1 has to be 1. If you recall the until criterion, this is our phi1, this is our phi2. If phi1 until phi2 is 1 and phi1 is 1 and phi2 is 0, then in the next step phi1 until phi2 should be 1. Okay, so what about the next step? Suppose here the automaton sees P1, P2. Firstly, since XP1 is 1, the automaton has to see a letter that contains P1, P2. So from this state, there cannot be transitions out of the empty letter and the letter consisting only of P2. So it has to have a transition either on P1 or on P1, P2. Now where does it go? This and this have to be 1, and since P2 is true, any compatible state where P2 is true will have XP1 until P2 to be 1. Okay. Now what about this position here? This says that this is a guess about the next letter. So here you can either say 0 or 1. And we have assumed it is 0. Since we have assumed this to be 0, the next transition should not contain P1. It should be either the empty letter or the letter consisting only of P2. And here it has to be 1 here, this has to be 0 here, and here it has to be 1 because P2 is 1, XP1 until P2 should be 1, and here this could have been either 0 or 1. Here the automaton has guessed 1 and so on. The idea is same. You look at the sub-formulae, remove all incompatible states. You look at all the compatibility criteria until and not, and then remove incompatible states. Some compatibility criteria like the X and until have a condition for the next step, and this can be ensured by defining the transitions appropriately. For example, if here you have guessed that XP1 is 1, then from this state the outgoing transitions will have to contain P1. Here if you have guessed that XP1 is 0, then the outgoing transitions should not contain P1. So this is the idea of construction for XP1 until P2. We have seen the algorithm for P1 until P2, and we have given an idea for XP1 until P2. In the case of P1 until P2, we also saw the final automaton that is constructed. In XP1 until P2, we gave some ideas as to what the states and transitions should look like. Let us now sketch the construction for an arbitrary LTL formula phi. Step 1. List down the sub-formulae of phi. You can go back to the slide with the expansions and you can see that the first step in the expansions was to list down the sub-formulae. In the case of P1 until P2, you had P1, P2, P1 until P2 as the sub-formulae, and this gave rise to many states. Here in principle there could be 8 states. For XP1 until P2 there could be in principle 16 states. Step 2, on these states check the and not and until compatibility. Go and look at this and not compatibility. This says that if the entry for phi1, the entry for phi2 and the entry for phi1 and phi2 should be compatible with respect to and. So if phi1, phi2, phi1 and phi2 are sub-formulae of phi, then the values in the columns should be compatible. Similar for until. For example, P1 0, P2 0, but P1 until P2 being 1 is incompatible. Similarly, P1 0, P2 1, but XP1 until P2 0 is incompatible. So based on this compatibility criterion, remove all incompatible states and add this new state Q0, which will be our single initial state. Okay, Step 1, you listed down the subformulae and made states which look like columns. Now from these columns, remove the incompatible ones. You will now get a set of compatible states. These are going to be the states of your automaton. And to this set of states, add this new state Q0. Next step. To define an automaton, you need to give the states, the transitions, and the set of accepting states. So far we have given what are the states. What about the transitions? Add your transitions so that the word compatibility, X compatibility, and until compatibility are satisfied. For example, in this state, xp1 is 1. So, the letters out of this state should contain p1. If it is p1, p2, then you should go to the state where both p1 and p2 are 1. And any compatible state where p2 is 1 would have this to be 1. This ensures word compatibility. This ensures the fact that here there is xp1 and then you are reading p1, p2, that is it contains p1, ensures x compatibility. And here this is for the next step. So this could be any value. You could either make this to be 0 or 1. So on P1, P2 there are two transitions. Either you could go to 1101 or 1111. So the transitions can be added in such a way so that the word X and until compatibility criteria are satisfied. From Q0, which is going to be the initial state, add compatible transitions, as in add word compatible transitions in which the last entry is 1. Similarly here this could have been either 0 or 1. However, the last entry has to be 1. From Q0, you always go to a state where the last entry is 1. This is for satisfying this condition about accepting expansions. If you look at any accepting expansion, the first column, last row will be 1. So this is step 3. From step 1, 2 and 3, what we have done is we have specified what the states are and we have specified what the transitions are. We still need to ensure the until eventuality condition. As you saw in the P1 until P2 example, we need to define accepting states in such a way so that it's not true always that phi1 is true, phi1 until phi2 is true, but phi2 is never true. You should never reach a position from where you always see this particular state. So, and there could be many until formulas. There could be many until subformulas. For example, in the subformula P1 until P2 and P3 until P4. For example, if there are many atomic propositions. Or something like P1 until P2 and XP1 until XP2. Things like this. There could be many until formulae in one LTL formula. For each until, you need to ensure the eventuality criterion. So what you do, for every until subformula phi1 until phi2, define the set of states f phi1 until phi2 as the set where either phi1 until phi2 is 0 or phi2 is 1. Let me explain this with the example of P1 until P2. P1 until P2 was a subformula. F P1 until P2 will be the set of states where either phi1 until phi2 is 0, in which case it's fine, or phi2 is 1. So the states that we have eliminated will have phi1 until phi2 to be 1 and phi2 to be 0. So such states are eliminated from the set of accepting states. So for every until subformula, you define f P1 until P2 to be the set of states where phi1 until phi2 is 0 or phi2 is 1. This will be the accepting set for phi1 until phi2. Any run that visits one of these states infinitely often will satisfy the until eventuality condition. Here is the final automaton. Step 1, we look at all compatible states. We list down all the subformulae, and then this will give rise to many columns which are going to be our states, and we remove incompatible states. And to this set we add a new state Q0. This is giving us the states of the automaton. Step 2, build compatible transitions. Transitions that are compatible with the word and not X until criteria. If the LTL formula does not contain any untils, then you can make every state to be an accepting state, because these two conditions already satisfy the properties needed for an accepting expansion. Only until has this extra eventuality criterion. So for each until subformula that is present, we defined a set of accepting states as shown in the previous slide. If no until subformula, every state is accepting. Otherwise, there are some until subformulae. For each until subformula, define an accepting set. So this will be a generalized NBA. A run would be accepting if some state in each of these FIs is visited infinitely often. And if that is the case, for every until formula, the eventuality criterion would be satisfied. We have seen in Unit 6, Module 4 that every generalized Bucci automaton can be converted into an equivalent Bucci automaton. You could refer this module to see the procedure. In general, the algorithm that we have mentioned could give automata which are exponential in the size of the formula. Because what we do is that we list down the subformulae and then we look at all possible values. There might be incompatible states, but in principle, this could lead to an exponential size for the automaton. Over the years, many algorithms have been proposed which perform better than this algorithm. However, it has been shown that there are some LTL formulae for which any algorithm will give a Bucci automaton with exponentially many states. This finishes the explanation of the classic LTL to Bucci automata construction. The best way to understand this algorithm is to work it out on many small examples.